So we have started recording. Okay, so I have seen that you have you have understood some concepts of the graphs. In fact, quite a few things, and you have done some assignments also. So let's recall the notations. This is just one slide, and obviously I'm not going to recall everything that you have done. Let's recall the notations that a graph G consists of a finite non-empty set of vertices. In Harare's book, he calls it a points. Okay, but we'll call it vertices. Sometimes I may end up calling it nodes. Okay, so a finite non-empty set of vertices V, and so these are the, let's say, vertices of a graph, and a set of edges. The set of edges is typically denoted by E. In some places, they also call it lines, but we'll mostly call them edges between the vertices. All right. So maybe, these are the edges between the vertices. We typically denote the graph, also graph G, also by G in bracket V E, right? So given the set of vertices and given the set of edges. Okay. So two vertices are called adjacent if there is an edge between them, right? So here U and V are adjacent, but V and X are not adjacent. Similarly, two edges are called adjacent if they have a common vertex. So the edge UW and let's say VW, they are adjacent because both of them are incident. So there's also another terminology, incident on vertex V, vertex W. Okay, so these are the things you know, and the graph I have drawn here is actually an undirected graph. So one can think of the edges as unordered pairs UV, where U and V both belong to the vertex set. You can also, so they are unordered pairs. So UV and VU will mean the same because it's an undirected graph. But for a directed graph, well, of course, we will not see directed graphs for most of our course, but just to know that for directed graphs, the edges are actually ordered. So this on this with the same vertices and similar looking edges, this is same vertices and similar looking edges. This is a directed graph, right? Where we have simply directions for each edge, and we can also have an edge from, let's say, Z to Y as well as Y to Z, right? Some people denote this by just arrows in both sides. One can also denote them, draw this by an arrow like this and a separate arrow on the other side. Okay, so this much I just assume that you know. So the concept we will start with today will be isomorphic graphs or graph isomorphism. Have you covered this? Hopefully not, right?
No, sir.
No, sir, we are not covered.
No, sir.
Okay, good, fine. So we'll cover this topic today: isomorphic graphs or graph isomorphism. So two graphs. Let's call one of them G1 with V1 and U1 as vertices and edges, and G2, V2 and E2 as vertices and edges, are called isomorphic if there is a one-to-one correspondence between their sets of vertices, preserving adjacency. Now, do you know what is a one-to-one function? Bijective function? No? Do people know what is a one-to-one function?
Yes, sir. Yes, sir.
Okay, people know, right? Okay, fine. So that's what we mean here. That means that, in other words, there is a bijective function f from V1 to V2. So the vertex set of the first graph to vertex set of the second graph. You can also write the other way because it's a bijective function, right? Such that, what do you mean by preserving adjacency? If there is an edge in E1, if there's an edge between U and V in the first graph, right, then the image of these two vertices will also have an edge in the second graph, and vice versa. So it's a bijective function. So if u and uv is an edge in the first graph, if and only if the fu and fv will also be an edge in the second graph. All right. So we also write G congruent G2 or G isomorphic to G2, or sometimes loosely we might just simply say G1, sorry G1 isomorphic to G2, or we might simply say G1 equal to G2. So let's look at examples. So let's say this is G1. I have even named the vertices. By the way, graphs can be labeled or unlabeled. It doesn't really matter. We'll see. So in sometimes I will draw a graph which has names in case I need to give the vertices some names, and sometimes we'll actually not give it labels. Okay, folks, just a thing, usually be on mute. That way we will not have a background noise. Of course, I can mute you, but be a little bit careful so that we don't have interruptions. Just be on mute, and when you need to speak anything, just unmute yourself and speak, and then again mute yourself. Okay, so let's say this is a graph G1, this is a graph G2, and this is a graph G3. So the question is, which of these graphs are isomorphic to each other? So let's think about it. You can see that the vertices are exactly vertices not exactly the same, but vertices pictorially look the same, right? So pictorially, the vertices look in the same positions. Okay, ideas, especially those who have not seen this concept before. It may be that some of you have seen it. They don't have to speak, but those who have not seen this before, do you see from the definition of isomorphism whether G1 is isomorphic to G2?
No, sir.
Okay, why not?
Because UV in the H in G2, but in not G1.
Well, UV is not an edge in G2. That's what you mean, but it's in edge in G1. No, that's fine. It doesn't have to be an edge. The same thing, because we can have a mapping from one set of vertices to another, right? So let's actually think whether G1 is isomorphic to G3. Let's look at that first.
Yes, sir.
Yes, it is.
Yes, sir.
Okay, why?
X can be mapped to U. W can be mapped to
X can be mapped to U.
X of G1 can be mapped to U of G3.
Okay, X can be mapped to U, right? Yeah, right. W can be
W
mapped
can
to
be mapped to W.
W. U can
V
be
can be
mapped
mapped
to
to X
X, and V
and
to V, right?
U
Yeah,
to V.
right. So basically, you see that this is just a chain, right? So this is just a chain, and that is also just a chain. Now, these are things we are talking more vaguely, but we will actually prove these things, right? So UVWX is just one chain, and UWXV or VXW, whatever way. So you can actually define a map like this. Now, this map I have written here may be a little bit different from what Shamrita said. Um, in this case, what I have done is U maps to U, V maps to W, and W maps to X, and X maps to V. Doesn't really matter. Okay, why is this preserving the adjacency? Well, U maps to U and V maps to W. Here U and V have an edge, so here U and W must have an edge. Similarly, you can just check for the other sets pairs of vertices, so that these two have an edge here, they will have an edge here, and so on, right? So is it clear? So that G1 and G3 are actually isomorphic. However, G1 and G2 are not, or G2 and G3 are also not. Let's leave that point a bit for now. Why they are not isomorphic, we'll come back to it a little bit later. But do you see some intuition why they are not isomorphic? I'll just give you the intuition right now, and we'll formally come back to this little bit later. Look, here, uh, this is more like a chain, and this is one at vertex at the center, which is connected to, which has an edge to all three other vertices, right? So this looks different. So essentially, two graphs are isomorphic if they can be made to look the same, right? Intuitively, that is the idea. So let's move on. Let's look at these graphs. Which of these graphs are isomorphic to each other? Okay. Um, well, so you can actually spend some time looking at it, but what is easy to see is, look, this is actually a bipartite graph. I know you have done bipartite graphs, right? So this is actually a bipartite graph, right? So only edges across, and three each vertex has three edges across the other side. And look at this one. So this one has vertex that has edges to these three, but not to these two, right? So if you think of this one, and this one as one group, this one, and this one as another group, you will actually see that you can simply redraw this graph as this. Okay, you can do the same for this also. So actually, what it turns out that all three of them are also isomorphic. So unless a graph is very small, like the one we saw previously, it's a small chain, 3, 4 vertices and things like that, it may not be immediate for us to recognize visually that graphs are isomorphic, right? But yeah, I mean, so it may not be so easy to recognize, but often two pretty different looking graphs can be isomorphic. Okay, so have you got?
Can I
Yes.
can I check with degree using
Yes.
degree?
Yes, you can. So that is exactly what we are getting to. You can check. You can do some checks, but it will not be completely foolproof. So let's get to that. Okay. So obviously, what you understood here is that here the degrees are important, right? Here the degree 3, every vertex is degree 3. Here also every vertex is degree 3. Here also. So looks like degree has something to do with it, but let's get to that slowly. So graph invariance. So an invariant of a graph is an attribute or a property. It can be a number, it can be a sequence of numbers or something like that, right? So it's a measurable property associated with the graph, such that the attribute remains the same for all graphs isomorphic to G. That means uh, if two graphs are isomorphic, that attribute has to be the same for both graphs. Then we'll call that property a graph invariant. Yeah, Nikhil, you have a question? Okay. So obviously, now this obviously, I will actually leave this obviously as an exercise for you. Obviously, the number of vertices and the number of edges are graph invariants. What do you mean? If uh, G1, G2 have different number of vertices, then there cannot be a bijective map between V1 and V2 anyway, right? So that's a straightforward thing to look at. Now, if the number of edges are different, then also no map can be adjacency preserving. Now, this is more like a hand waving statement, and you have done a lot of classes on proof techniques and so on. So please, if people have, uh, mm, if people think they need practice with proofs, please prove this. So if two vertices have the same number of, if two graphs have same number of vertices but different number of edges, then they cannot be isomorphic. So just practice this proof if you want to. Okay. Now let us try to. So these two are graph invariants. That is fine. Let us try to investigate some more attributes which are invariants. So, and one of the things that one of you said, can we check with degree, right? So let's try to see. Now, for this, before going into that, let's go back and look at our example of G1 and G2, right? We kind of said that these two graphs are not isomorphic, right? And why? So let's, it looks visually that they are not isomorphic, but we also saw that visually two graphs may be very different looking, but they can actually be isomorphic. So let's see why these two graphs are not isomorphic. So these two graphs have the same number of vertices and same number of edges. Both have 4 vertices, 3 edges, right? So those two invariants are satisfied, right? So those two invariants are satisfied, but still we are saying they are not isomorphic. Now suppose the graphs are actually isomorphic. Then what's the problem? So then there should be a bijective function from this set of vertices to this set of vertices, right? We should be able to find on map like the one we were talking about. Now consider the inverse image of W here. That means some vertex from G1 must go to the W in this, right? So there should be someone which goes from this to this W. So which one? Okay. So one of them have to. Now the point is in V2, W is adjacent to 3 other vertices. So in V2, W is adjacent to 3 other vertices. So if we have a map, then the inverse image of W also must be adjacent to 3 other vertices in the first graph. But there is no vertex which is adjacent to 3 other vertices. Yeah, so there is no vertex which is adjacent to 3 other vertices. So W cannot actually have an inverse image satisfying our condition. Clear? Why these two graphs are not isomorphic? Okay, so then G1 and G2.
Yes.
Yes. Okay, so I think it's clear. So then these two graphs are not isomorphic. Let me clear this. So this means that just the number of vertices and number of edges will not be reliable at all. In fact, it will turn out that nothing will be reliable completely. But as we said, can we check with degrees? So let's get to that. So the intuition is if two graphs are isomorphic, then there must be an one-to-one correspondence between the degrees of their vertices also. Because here we had something of degree 3, but because we do not have anything of degree 3 here, we can right away say that they are not isomorphic. So this leads us to the concept of degree sequence of a graph. The degree sequence of a graph is the sequence of the degrees of its vertices. Now, the sequence you can, for example, this has degree 1, this has degree 2, this has degree 2, this has degree 1. You can write 1, 2, 2, 1, and another person may write differently in different order, right? So just to make sure that we can compare two degree sequences, the convention is to order them in monotonically decreasing order. Okay, descending order. That means you would write the largest degree first, highest one first, and then decrease and so on. Of course, the degree can repeat. Multiple vertices may have the same degree, right? So again, let's look at the examples. So what would be the degree sequence for this graph?
2, 1, 1.
Sorry, again?
2, 2, 1, 1.
2, 2, 1, 1, right? So this is 2, 2, 1, 1. And this one?
3, 1, 1, 1.
3, 1, 1. Very good. So the degree sequences are like this, and the degree sequences are different here. So verify for yourself that when two graphs are isomorphic, then they have the same degree sequence. Okay, they must have the same degree sequence. That intuitively looks very easy, but still verify for yourself with a formal proof. But the other one is more interesting. The converse is not true. So if two graphs have the same degree sequence, it does not necessarily mean that the two graphs are isomorphic. Okay, so as one of you said, can we check with degrees? Yeah, I mean you can check for non-isomorphism if you get a difference in the degree sequence. But if the two graphs pass this test also, it will not be guaranteed that these two graphs are actually isomorphic. In fact, I'll give you a bad news here. The bad news is, so people have tried, right? People have tried to come up with tests for isomorphism. So obviously the most trivial ones would have been number of vertices, number of edges, and then as we figured, naturally the degree sequence comes in and so on. So they are all invariants, right? So the question is, can we list down a number of, or list of invariants, and if we check them for two graphs, if the number these invariants are all same for both graphs, then can we say that the two graphs are definitely isomorphic for general graph? Not for very small graphs of size 2 or 3 or something like that, but for general graphs. Well, the thing is, nothing is known about it. So there is no known list of invariants which will guarantee you that two graphs are isomorphic. Okay, so but nevertheless, you can check by degree sequence and other things that two graphs are not isomorphic. So that way you can do. So next is subgraphs. Have you covered subgraphs in the previous classes? Okay, maybe not. But anyway, so the concept is easy, so it's not
The graph with all the vertices and the subset of the edges.
Right. Have you covered it in the previous classes?
I don't think, but yeah, I remember.
No, sir. Actually, Shobham sir did not start graph portion.
That is fine. I know that. I just because I think it was not covered. That's how I prepared it. But I'm just.
Sir, these slides are present on the website or web page.
Which slides?
Is this slide that you are just posting on the screen?
No, not yet. But they will be. I will provide you the slides and probably show me, or somebody will post it to the website also. Okay. Okay, so I'm just asking you sometimes because I'm taking over from I have not been part of the course so long, right? So that's why sometimes I'm asking you. Of course, some of you may know certain things, but I'm asking you just to verify whether this has been already covered in the course. Then I will go faster, and it will be a quick recapitulation. If it has not been covered, then I know how to go about it. Okay, so subgraphs. So a subgraph of a graph G. So let's call the subgraph G1. Okay, so subgraph G1, which will have V1, E1 of a graph G, is a graph such that is a graph such that the vertices are also subset of the original vertices, and the edges are also subset of the original edges. All right. So then G1 is a subgraph of G, and G is a supergraph of G1. It's just like subset, but subset in both vertices and edges. Now, that's just a general subgraph, but there are particular concepts inside that. But let's just look at one example. So this is G, right? And this is G1. These faded ones are just to show you what was in G1, but not in G1, right? So this is a subgraph and this is a supergraph. Note, it's possible that all the vertices are present, but not all the edges. It's possible that, well, the other way is not possible, that all the edges are present, but okay, that's also possible if the graph is not connected, right? So that is also possible that all the edges are present in the subgraph, but not all the vertices. Because if there is some isolated vertex without any edge, you can drop it and make it a strict subgraph, but you still retain all the edges. So basically, it's just a subsetting kind of a thing. Now, the more interesting concept is spanning subgraph. So what is a spanning subgraph? A spanning subgraph is what one of you are actually saying. The spanning subgraph is G1 is a spanning subgraph of a graph G if it covers all the vertices. So you don't need to have all the edges, but cover all the vertices. Okay, so spans all the vertices. So in other words, all of the vertices of the supergraph must be present in the spanning subgraph, but all the edges need not be present. So let's look at this, and this is actually a spanning subgraph, right? So you see all the vertices are present, but we can actually drop some edges. Now there is the so this is what we are doing here is we are just making sure all the vertices are present, and next what we will see is we'll drop vertices, but we'll make sure that all the edges connected to those vertices are present. So induced subgraphs are exactly what are actually those where for a graph, now consider that you want to drop some vertices. I mean, may not be like an operation, but it's considered a subset of the vertices. So let's the subset be V1. The graph consisting of V1 and all the original edges that are incident to vertices in V1 is called the subgraph induced by V1. That means if a vertex, if you keep a vertex from the original graph, then all the original edges incident on that vertex also must be there. So if you keep a vertex, keep all the connected edges. Okay. So and then it's you can see that it's also a maximal subgraph of G with vertex sorry, with vertex set as V1. Let's look at the picture again. And maybe I'll spend a little bit of time here to keep the make the concept absolutely clear here. So this is G and this is same. Okay, so far I have not removed anything. Let's say I actually don't have these two, W and Y. Suppose I don't have this. Then which edges will remain in my induced subgraph of U, V, X and Z? U, V will remain, right? V, Z will remain and X, Z will remain, right? So essentially, this will go. So if well, in some sense, this statement might be slightly misleading. That look, I mean, V had an edge to W, but if you remove W, obviously the edge is gone. So that will go. But since you are keeping U, V, Z, and X, any edges between these vertices must remain present in the induced subgraph. Okay. Or in other words, we're just kind of taking a subset of the vertices and seeing we restricted to this subset of the vertices, how does the graph look like? Is it clear? Is it clear to everybody? Okay, let's shall we just do another exercise here. Let's say I want to take from, okay, that was one example. Let's say I want to take another example here. So
Sir,
let's, yes.
Sir, what is the meaning of maximal subgraph?
Okay, I'll come to that. Let's first the word maximal requires a bit of attention, so I'll come to that. Now let's actually look at another case. So what would be the subgraph induced by the only vertex W? Let's say I want to see the W is a singleton set of vertices, right? So one vertex. What is the subgraph induced by only W?
That will be only W.
That will be only W. Very good. What will be the subgraph induced by W and X? That will be just these two vertices separate, right?
Yes, sir.
Just separate, right? And then what would be the subgraph induced by W, X and U? So that will be this edge.
U to W H.
And this is separate, right?
And the one vertex.
Right. Okay. All right. So I guess induced subgraph is fine. Now let's talk about maximal. Okay. So let's first understand what we mean by maximal in general. Maximal and maximum, these two are different things. Have you studied this in any of the, maybe the discrete math or the algorithm course in this semester already? The meaning of the word maximal? Okay, no. Let's do this anyway. Let me see if I can explain this with an example. Suppose we want to talk about a property, okay? And let's say the property is property of a set, let's say we want to talk about a property of a set, I would say the set satisfies the property if uh, mm, if uh, if the set of integers, let's say a set of integers satisfy a certain property if all the numbers are between 0 and 10 and all the numbers are distinct. Okay, so all the numbers are between 0 and 10 and all the numbers are distinct, then I would say the set satisfies the property that I want. Now what would happen is, suppose all the numbers are already there. Okay, then if you add any more number, either it will not be distinct or it will have to be outside the range. So then it will not satisfy that property, right? So this set is actually maximal with respect to that property. Now, okay, all right. But the example I actually gave you does not distinguish between maximal and maximum in a sense. So maximal and maximum cardinality, let's say, yeah, okay. So let's say another set. Let's talk about this. Let me actually write it down. So I will say a set of numbers are co-prime to each other, right? So let's say a set of numbers are, so let's say my 2, 3, 4, 5, 7, and 10. So this is a set. Let's say I have a set. Now I want to take a subset B of A such that, let me, just a moment, let me remove these things. Yeah, so this I have now more space. So let's say I want to take a subset B of A such that the numbers in B are okay. Do you understand what it means? Does everybody understand what it means? So let's say B is equal to 2, 3. Okay, is it a valid subset according to this property?
Yes, sir.
It is. What about 2, 4?
No, sir.
No. All right. So you see that some subsets actually have this property and some subsets don't. All right. Now let's try to look at the following one. So 3, 5, 7. Okay, 3, 5, 7. 3, 5. Okay, so 3, 4, 5, 7. Okay, so let's take this. Now, if you increase this any further, right? So if you add any more element here, then will it remain?
Not co-prime.
It will not be co-prime, right? So then this is actually a maximal subset which has this property. But let's see whether I have been successful in getting the right example. It is possible that a subset is maximal but not maximum cardinality. You can still have another subset which is bigger than this with this property, but on this subset you cannot add anymore. So let's actually try that. So B is equal to, in this case it will not be possible. I need to, so in this case I think because I have made 2, 4, 5, 10. Okay, so what about this 2, 3, 7? Okay, this is also maximal, but I'll leave this as an exercise for you. You can actually construct something such that you may have a subset of size 4 which has the property, but another subset of size 3 which is also maximal. That's possible. So what we mean here is maximal subgraph of G with vertex set as V1 is that if we have this vertex set And if we add any more edge here, so let's say if I add the edge uv here, let's say I add the edge uz here, then it will not be a subgraph of G anymore. Get it? This is a subgraph of G, and the vertex set is V1. V1 is U, V, Z, and X. But if I add any more edge on this graph, then it will not remain, or maybe I add this, it will not remain a subgraph of G, because all the edges I could take from G I have already taken. Any more edge will mean that it is actually going beyond my supergraph that I'm considering. Clear?
Hello.
Yes.
Sir, if we add when we added an edge from U to Z, then I mean, is it necessary that the labels should also be the same for a subgraph?
I mean, up to isomorphism, it is not necessary, but typically, look, I mean, sometimes we will consider things modulo isomorphism. We will say two graphs are same, but here we are not. We don't need that. Typically, for a subgraph, we mean okay, we are keeping the labels same because we want to show it as a subgraph of another. But if you want to change the labels, then this will be a subgraph of another graph which is isomorphic to this. So ultimately, it's the same thing. You don't get anything new.
Okay. Yes.
Okay. So now the maximal thing is clear, right? So let's move on. So that's the induced subgraph, and this is the this is a subgraph induced by U, V, X, and Z. Okay. So yeah, I think I will only cover a little bit of the trees today, and then that's it for today. We'll stop. And then from next class onwards, we'll actually take nearly 2 hours. So trees. You have proved a lot of assignments, or not a lot, maybe a few assignments or exercises regarding cycles, right? So cycles, paths, you have done these things. I just noticed in the assignments. Now, a connected acyclic, that means has no cycle, graph is called a tree. Okay. Any graph without a cycle is called a forest. And then obviously or naturally, components of a forest are trees. So any graph without a cycle is a forest. We'll see why that looks like a forest though. But this doesn't say that it's connected, right? So it can be disconnected. So then if you look at the connected components, disjoint components of that forest, then we should get a tree. Okay, so let's look at what a connected acyclic graph looks like. So maybe it looks something like this. Okay, so there should not be any cycle at any point of time, right? So it's actually like a tree, right? So like, and this is the root, right? And these are leaves. Now, and these are neither the root nor the leaves, but yeah, so you see this. Now, one point here, from this picture, is it necessary that this has to be the root? Can any other vertex be the root? What if, I just change this vertex? What if I drew this graph slightly differently? And what if I, just put this one here and this one there? Then this one would have been the root and this one would have been a leaf, right? Okay. So the notion of root and leaves are actually that depends on what application you are looking at and how you are actually dealing with this particular graph. But nevertheless, roots and leaves of trees is something you will use a lot in your data structures and algorithm, and in if you do data science or anything like that later on, this will come in again and again. All right. Now, one point we want to mention here is that in computer science, however, we are more used to visualizing trees upside down. So instead of this being the root like this, we are more used to having the root at the top and leaves at the bottom like this. Okay, so let's just think of it as like this, and then this is the root and these are the leaves. Okay, so this is what a tree is, and it's a connected acyclic graph. Now, what we will do today is we'll look at some properties of trees, and we'll actually prove one of them, and then we'll stop for today and continue from the next class. So there are certain necessary and sufficient conditions for a graph to be a tree. Let us denote the number of vertices by V, number of vertices by P, and number of edges by Q. Then the following statements are equivalent. Of course, one is G is a tree, that means it's a connected acyclic graph. Any two vertices of G are connected by a unique path. You have done paths. Now, any two vertices of G are connected by a unique path. G is connected, and the number of, basically P is equal to Q plus 1. The number of edges is 1 less than the number of vertices. G is acyclic, and P is equal to Q plus 1. Okay, so you see, either it needs to be connected and this, or is to be acyclic on this. So you see, there are three things here. The definition says connected acyclic, but it is equivalent to saying connected and P is equal to Q plus 1, or it is equivalent to saying acyclic and P is equal to Q plus 1. So the fun part is any two of the three conditions will be enough: connected, acyclic, and this, right? So any two of the three conditions will essentially make sure that it's a tree. Okay, so let's actually prove the first one for today. Any two vertices of G are connected by a unique path. If G is a tree, then any two vertices of G are connected by a unique path. So if G is a tree, that means it's connected and acyclic. Then any two vertices of G are connected by a unique path. So let's prove. So since G is connected, tree means connected acyclic. So since G is connected, any two vertices have a path between them. Done. So path is done, but we need to prove uniqueness of that path. Now suppose the path, suppose there are some two vertices, okay, U and V, such that there are multiple paths between U and V. Okay, I mean two different paths at least, P1 and P2 between U and V. So it might look something like this. The picture is pretty general, though it doesn't. I mean, it will fit into anything. So it will help you to look at the intuition, but it doesn't really actually force you to a certain example or something. So you know that whenever you are trying to prove something, you cannot prove by example. So it's just a general picture here. So suppose from U to V there are two paths. One is P1, another is P2. What are these W's and W primes that I have drawn here? So let W be the vertex till which P1 and P2 are same starting from U. So let's say we are starting from U, although it's an undirected graph, let's go one way. So it's a starting from U and until till W, let's say the two paths are same. It's possible that the two paths are different from the beginning itself, then W is same as U, no problem with that. Okay, so let's say from W, the two paths go into two different directions for the first time. That means these nodes are not same anymore. Okay, there has to be some nodes which are different, otherwise two paths will not be different, right? So then let's say W is the last one after which they bifurcate for the first time. So since the final destination V is again the same, the paths must join again somewhere, right? Okay, since the final destination is again the same, the paths must join again somewhere, and let that vertex where they join next time is W. Now, it does not mean that they will join only once and then stay together forever, not like that. It can again bifurcate and again join and so on, but essentially what we are saying is after W, once they go apart, they join into one vertex for the first time in W prime. So W prime is the vertex after W, so that W first vertex after W. I should write the word first here after W, so that W prime is in both path P1 and path P2. Then what do we have? Then we have a contradiction, right? So you see the contradiction?
Yes, we will have a
Yes,
cycle.
Yeah, then we have a cycle, right? So we have a cycle W in segment of P1 until W prime, then W prime, segment of P2 till W. This whole thing is then a this thing is then a cycle, right? Yeah. So that's then the proof that if G is a tree, then any two vertices of G are connected by a unique path. All right. So yeah. So I think that for today that will be it. We will continue in the next class. We will continue with the other properties of trees. In fact, there are more than what I have listed in the previous slide. So there are basically other properties of trees, and we'll continue with the concepts of spanning tree. We have done spanning subgraph, and spanning trees are actually very interesting because you can cover the whole graph, but without any cycle. It's like, what is the minimum thing required to cover the whole graph, kind of a thing, right? Okay, so we'll continue on to that. So any questions as of now? Okay, very good. So I will let's stop the recording.